Good afternoon, ladies and gentlemen. You made it to the end, so thank you. And I hope you find this rewarding and informative and worthwhile for you to stay to the end. So I think I'm going to move away from this. I can speak loud enough. And talk about a very interesting project that took us a long time from conceptualization until execution and getting results. It's a long journey. My colleague, Dr. Mark Green here, will follow with me this step by step. It has been a long, maybe 15 years. The test itself took a few months, but it's about 15 years to get to this point. And the idea here is to do realistic fatigue using rolling loads rather than the pulsating loads that we are all familiar with using hydraulic actuators in the lab. So I would like to acknowledge the work of my student, Sibris Gao, who did his PhD on this topic. And if I may use this one here. And I will be talking about rolling fatigue of bridges reinforced by GFRP bars and GFRP protruded sections as stay-in-place forms for rapid construction. With this, moving forward, I think this is something we are all familiar with. Recent reports in Canada and the US shows the dire situation of many of our infrastructure. 38%, for example, in the Canadian infrastructure report of bridges, showing that they are actually rated as fair to very poor. Almost similar in the US, 42% are more than 50 years old, and these are relatively recent reports. So we are all aware of this. So what exactly is the point we are trying to talk about here? Not working. The typical fatigue we do in the lab using pulsating or fixed point stationary loads, you load and unload on the same spot in a vertical direction. And you do not have any lateral motion on the structure. This is the type of fatigue we are familiar with, and that's what most acceptable by many departments of transportation and ministries of transportation. If you reach 2 million cycles or 3 million cycles or whatever, that accepts the technology, whether it's a method of construction or a material of construction. But the reality that we know is that the bridges are subjected to lateral load. Truck load is fixed or constant. There is a dynamic effect, but the load does not depart the surface upwards. So is there a difference? That's the question we are trying to understand in terms of the fatigue behavior of these structures. Okay, so to start from first principles, if you think about a small element here on the bridge deck, and you have a load applied, then you have a set of principal stresses, compression and tension. When the load goes up, the principal stresses drops to zero. That is the fixed point pulsating load. That if you trace the principal tensile stress, which is a source of all problems in concrete, sigma 1, you find that it's a 0 to F1 fatigue. So the stress ratio is 0. Okay? Look at the second case. If you have the load sitting here, you get the same principal stresses on that element, right? Start moving the load to the next point. They switch. The stresses switch. The principal tension becomes principal compression. What happens to your fatigue cycles? You start cycling from negative to positive principal stress. So R is less than -1 for fatigue. We all know that materials are more, R -1 fatigue is more aggressive than R equals 0 fatigue in any material, right? So concrete is no difference. So right from the onset, we expect that this scenario will be more problematic. So I'd like to talk about the specimen design. So we designed a bridge deck that is, I would say, almost 4 meters. That's like what? 14 feet wide by 15 meters long, supported by steel girders with a girder spacing of 10 feet. This is a large girder space. It's common up to, I think, 12 feet or so, maybe more, but 10 feet will be one of the wide girder spacings. And it was designed according to the Canadian Highway Bridge Design Code, CHBDC, which is a model code used in many parts of the world as well. The thickness of the bridge deck is 210 millimeters. This shows my student Severus actually installing the sacrificial plate which was torqued to the steel girders, and the sacrificial plate is actually having the shear studs, designed exactly according to code, but we did not want to waste the whole beam, so we have a sacrificial plate and torqued very well to guarantee pretty much a full composite action between steel to steel. Okay? The spacings of the cross spacings, again, designed according to the CHBDC with maximum 8 meters between the cross spacings. This is a top view of the bridge deck. Although it was one integral bridge deck with a monolithic cast, conceptually it has different technologies embedded inside. Okay? So there are 4 equal sections, each is about 3.81 meters, so you have almost large square panels, all monolithically cast. But the reinforcement in each one of them is a bit different. So the 2 ends on the right, on the left, are identical with GFRP rebar, okay? Designed according to S6 of the Canadian CSA. The travel path of the rolling load starts from this point up till here only. This one was reserved for the conventional, traditional pulsating load with actuator like we all do all the time. So those 2 sections are a mirror image, so it's a fair comparison in terms of boundary conditions and everything else. This section was a controlled steel rebar, again according to code, top and bottom mesh. This section is an interesting design I'll share with you, which is actually the title of this presentation in your brochures you have for the conference, but that's a stay-in-place GFRP formwork. We also paid attention to the connections between one material or one technology and the other, and the overall and the overlap development lengths or splice lengths. Okay, that's the rebar section, GFRP rebar section. This is the stay-in-place form. The top shows you a summary of the reinforcement ratios. I just would like to point out one thing. Maybe I'll jump first, explain what exactly is stay-in-place form in this case, and then I talk about reinforcement ratios. So these are transverse I-beams, protruded GFRP I-beams, spanning the 10 feet between the supporting girders and spaced at a certain distance, 3 feet. And I'll talk about 3 feet wide. And then in between, spanning between them, is planks made of GFRP protruded sections, flat plates, rib plates with T-up shaped ribs for the pull to elbow. All of this is available off the shelf, no custom made, no custom manufacturing. So, and those are spanning and resting where? Resting on the bottom flange, not on the top flange. So everything is embedded inside the concrete deck. I'll show you a picture next. And then we put a top rebar. Stay-in-place forms are inherently positive moment reinforcement. You must have a negative moment reinforcement. So there is a top rebar mesh identical to this GFRP, sitting where? Sitting on top of the top flange. So the I-beam embedded inside is serving as transverse reinforcement, serving as support for a stay-in-place form, and serving as chairs for the top rebar at the same time. Okay? What controls that spacing here? 2 things. The transverse reinforcement ratio you want, but interestingly enough, the serviceability of the stay-in-place form under fresh concrete, under the weight of fresh concrete. Before the concrete hardens, it's carried by this plank. You don't want it to deflect and sag too much. And that controls the 3 feet space. Okay? Doing all this resulted in reinforcement ratios, but I just would like to point out that the number shown here, 4.7, is misleading for the I-beams. I think my student took just for the sake of presentation, took the area of the whole I-beam and allocated it for the transverse bottom reinforcement. The reality, there are two important factors. Number one, the I-beam is so deep into the section such that its upper half is top reinforcement. Bottom half is bottom reinforcement. That's number one. Number two, Young's modulus of the protruded fiberglass GFRP is 50%, roughly 30 GPa, compared to Young's modulus of rebar, 60 GPa. So if you actually, when we do transformed section analysis, transforming the GFRP I-beam into equivalent rebar with 60 gigapascal, and allocate half of it to the top, half to the bottom, and find the transformed section and the real centroid of reinforcement, it becomes actually 0.86, which is not much difference from rebar. It becomes 0.86. Okay, that's the end section with the GFRP rebar mesh top and bottom. We actually, for fabrication and casting and everything, we hired a contractor because of this significant, enormous size of that bridge. To our knowledge, that size of a bridge deck perhaps is the largest ever tested in the laboratory, let alone under a real truck in the lab running, right? So it's quite significant. So we hired professional contractors for formwork. We hired professional contractors also for pumping concrete and pouring and finishing the surface. This is the GFRP rebar mesh. A whole bunch of strain gauges everywhere, and you can see the machine a little bit in the back there. This is the stay-in-place form I was trying to describe to you earlier. This is the steel beam with the studs. This is the transverse I-beams, fiberglass, GFRP, protruded sections, a 6-inch by 6-inch section. Sorry. And that is the planks, ribbed plates, resting on the bottom flanges, and everything is embedded. Excuse me. Everything is embedded in the concrete, so the bottom surface is streamlined, and you cannot see any of that stuff. It's all internal reinforcement. Okay? You'll notice something interesting. This is the beginning of the section with rebar. So to facilitate the splice between the two reinforcement systems, we had to drill holes on the width of the last beam only, right? So the rebar coming from the other one embedded inside a development lens according to ACI 44 document. This is just the picture of the I-beams, the planks, and we have an interesting connection at the end, and that's where the I-beams resting on the bottom flange, the planks resting on the bottom flange. And we had, so the first question, what's the connection? Epoxy, and we actually used self-tapping screws as well. This is the whole thing with all the reinforcement before casting, and you can see the rebar, GFRP steel, stay-in-place forms, and GFRP on the other end. This shows you a quick real time of the casting and finishing the surface. I'm not sure if you can be able to see it. It's a little bit, but you can see basically the process. And all this happened while it's within the setup under the testing apparatus. And at some point, you see that the wheels, the tires are on our way. So we have to bring the tires back here. By the way, those tires, we found that if we use real tires, they are the same size and everything, and calibrated for the same footprint like H2. Actually, sorry, not like H2, like CHBDC, the footprint on the surface. But we found that if we use the real trucks of, the real tires of trucks, Doug is sitting here. Doug was the project manager back then for this machine when he was a PhD student, Doug Tomlinson. We found that the real tires of the trucks will burst within, like, every week I have to change the tire for 3 million tires, right? So we found that those tires, those beasts that push the aircraft out of the terminal, which are 747, those tires are like an inch thick with nitrogen inflated. So they last for a long time. But were calibrated to give the same contact on the surface. Okay, this is the bridge deck after the cast. And these are some of the specs of the machine. So this is a 2 half axles two half axles, dual tires, 2 tires each, spaced at 4 feet, but you can actually adjust the second one and flip it around. You can get 8 feet if you want spacing between the axles. It can run, it can carry a load. Each of them can carry 125 kilonewtons, total of 250 kilonewtons, 25 pounds or so. And it can run up to a maximum speed of 6 meters per second, but that will happen only at a single point. The system has an inherent lack of efficiency because it's linear. You must start from 0 velocity and must end with 0 velocity to reverse. So it goes in a ramping speed up to 6 and then decelerate to 0 and come back. It's not a constant speed also. If you want a constant speed, you have to build an extra ramp and end up with a ramp, and you have to have a lower speed to have a constant speed. We tested the speed within that range of 6 meters per second. Up till 6 meters per second, it doesn't make any difference. 6 meters per second is really not any close to your highway speed, but certainly in the lab, when you see this thing running at 6 meters per second indoors, it shakes the whole safe now. Okay, I think I showed this before. That's the idea of how it works. You have a hydraulic actuator here and the lever arm 2 to 1. If you pull up 1 pound, you get down 2 pounds. Okay? And then that's the vertical loading. The horizontal motion is by a conveyor belt and a motor. This is a top view of the range of motion. Those are the 2 half axles. This is the footprint of 2 dual tires, spaced at 4 feet. It reaches only up till 1100 millimeter from the edge. We did not have an end beam for torsional effect at the end because we knew that we're going to stop 1100 from the end, but it passed the mid span of the end section. It passed the mid span of the end section. And then goes all the way to here, again 1100, to avoid overlapping effects. And this is the pulsating load machine, the part using a hydraulic machine. This is just a quick video showing the operation. There was nice music. Okay. So I'm just, for the interest of time, I'm showing you some snapshots and the key conclusion really, rather than there's tons of details of results here, but I'm not going to go through this. This is the rolling load. Those are the 2 end sections. One is rolling load and the other is fixed point pulsating load, identical GFRP rebar bolts. And here is the, so every few hundreds of cycles, we stop and do a monotonic test to get the stiffness. So this is the first cycle, of course, is when the first cracking happens. And then cracking stabilizes. So you find that it becomes linear in the second and subsequent cycles. Okay? So every time we stop, we measure the load deflection, right? You notice 2 things. The slope of the curve reduces. That's part of the stiffness degradation. And because the stiffness is reduced due to degradation, the effect of just self-weight alone becomes higher deflection because your EI has changed. And that explains the propagation of deflection along the horizontal axis. Same thing, of course, happens with the pulsating load. This is a typical actuator load, whereas these are points because we have to run the machine at incremental load level and measure the deflection. That's why we have discrete points, whereas this is a continuous, as you are familiar with from actuators.
What are the values of it?
Oh, that's the number of cycles when we stop to do a monotonic test. So for example here, after 10,000 cycles, we stopped and did a quasi-static load deflection. Anyways, that we did this up to an equivalent 3 million cycles. And so what I'll do now is I'd like to plot the ratio of the slope of each of those lines to the slope of cycle number 2. I did not take cycle number 1 because of it's an uncracked section. Okay? So I took cycle number 2 as K0. Yeah. And then we plot that slope relative to this for all of them and see what happens. This is the pulsating load, and this is the rolling load. Right away, you can tell, and that scale is actually just regular linear scale. You find that the stiffness degradation is much higher for the rolling load compared to pulsating load. If you do that on a logarithmic scale, which is often the way to plot this, the same data, just put it on a logarithmic scale, you notice something very interesting here. This is at 3 million cycles. The rolling load suffers more degradation than the pulsating. If you just would like to establish an equivalency, right? You take that point here, and you find here you get the same level of cumulative damage or stiffness degradation as at 25 cycle compared to 3 million, right? So that tells you that roughly the damage happening from one rolling load, as in real life, is about equivalent to that of about 120 of those we do in the lab. Later on, we extrapolated this and we established a conversion factor to help people to converge. Most people will be able to do the pulsating load only. Okay? This is a cracking pattern from the underside. The stay-in-place form, you cannot see anything because obviously that's the way it is. And this is the rolling load, and this is the pulsating load. This is the steel section, which I haven't spoken about today at all, the steel reinforcement section. But that's GFRP rolling versus GFRP pulsating. Clearly, the intensity of cracking here is damage is spread rather than being localized. Something very important and very interesting we found. The cracking underside is also pitting, right? The volume of rubble after 3 million cycle on the floor under the deck was enormous compared to the pulsating load. And we found a lot of pieces fell off because there is a grinding effect as the load moved from one side to the other of the crack. Okay, again, stay-in-place form, I'm going to jump quickly. That's the GFRP rebar compared to GFRP stay-in-place forms. The stiffness degradation, again, comparable. As a stay-in-place form, which is the red blue curve, performed the same or even better than the GFRP rebar. And we are currently doing some numerical modeling using LS Dyna to capture the moving load effect on the bridge. And you can see the load going back and forth. I'll skip this and move on to the conclusions, which is only one. Okay, that's the load returning back. Okay, very simplistic conclusions because there are lots of details that I'm not going to talk about today. Rolling load is way more aggressive than pulsating load, period. Okay? And we found that one cycle of rolling approximately is equivalent to 120 of the pulsating, and the stay-in-place form actually worked very well. It matched 3 million cycles to same like the GFRP rebar and could speed construction. Thank you very much. I acknowledge the Ministry of Transportation of Ontario and B-Rod Focal who donated some material for this project. Thank you.